In this experiment, the goal was to see how varying speed, shape, and dimpling will affect the coefficient of drag. Looking at the past, the present, and the future, it can be seen that car design has gone through many changes and has become more aerodynamic through the years. Now, the need behind this is to tackle the issue of low coefficient of drag and fuel efficiency. The team's capstone design was to build and design an aerodynamic vehicle for Shell Eco Marathon, which has a low coefficient of drag. That is the inspiration behind this experiment.
The first factor that will be varied in this experiment is the speed of the moving air from the wind tunnel. From literature review, it was observed that for a particular design, that change of speed of the moving air will have no effect on the coefficient of drag of the vehicle. The second factor that will be varied in this experiment would be the shape of the body design itself. From literature review, it was determined that the more aerodynamic the body, the lower the coefficient of drag will be experienced by this body. The third factor in this experiment was considering to have dimples on the vehicle body or not. From literature review, one would expect that in the case of dimpled bodies, the dimpled body would experience a lower coefficient of drag when compared to a body that is not dimpled. However, that is not the case from literature review.
And now we will talk about the experimental apparatus and the test procedure. The equipment used in this experiment were the HM170 wind tunnel by Gunt Hamburg, the Prusa i3 3D printer, the Fortis 400MC 3D printer. The standard followed while using the wind tunnel was the SAE J2084 standard for aerodynamic testing, while the standard followed while using the 3D printer was the ISO TC261 standard for 3D printing. The population for the experiment was considered to be all the 3D printed SEM prototype vehicle body designs whose drag coefficients will be measured using the Gunt HM170 wind tunnel. The first part of the experiment was done to test for the effective wind speed on the drag coefficient. Design A was tested at three speeds, 5.6 meters per second, 11.1 meters per second, and 16.7 meters per second. Design A was modeled on SolidWorks, and then the model was exported to 3D print. A 4mm hole was drilled in the center of mass of the model, so that the metal supporting rod can be fitted in the model. The 3D printed model with the rod was fixed in the wind tunnel, and testing began. 5 trials were done for each speed.
The drag force was plotted against half rho AV squared. A linear trend line was added to the graph, and the R squared value was found to be 97.5%. This suggests that 97.5% of the deviations are accounted for by the model. The gradient of this line is drag coefficient according to the formula force is equals to CD times half rho AV squared. This means that CD is constant with changing velocity. It is concluded that drag coefficient is independent of speed. Therefore, for the next part, only high and low speed values were tested against.
The second part of the experiment was done to test for the effect of the car shape and dimples on the drag coefficient. Designs A, B, and C were tested at two speeds, 8.3 meters per second and 16.7 meters per second. It is important to note that for the different designs, the frontal area was kept the same. The same process was used to set up and test the three different designs as the first part.
Once again, the drag force was plotted against half rho AV squared for the three dimpled and non-dimpled designs. Linear trend line was added as the relationship between speed and coefficient of drag was known. The coefficient of drag values were recorded, and the bar graph shows the results. It is observed that design A has the highest coefficient of drag, followed by design B and then design C. Dimpled car designs were found to have had higher coefficient of drag than the non-dimpled for all three designs, as expected from literature review. Next, binary values were assigned to the different variables as shown. Using data for coefficient of drag, the general linear model was determined. Next, the average effect of the variables were calculated and used to plot a Pareto chart. From the chart, it is observed that design C has the highest effect on coefficient of drag, followed by the dimpled. Next, an unpaired t-test was carried out on all the data for low speed and for high speed. The confidence interval was found to be 20%, which suggests that the chance that the difference between low and a high speed is actually zero but has a value of 0.011 by accidents is about 20%, which is not a very small value. Therefore, it can be said that it is quite likely that low speed has higher coefficient of drag than high speed, but not by much. Next, a paired t-test was carried out between the two speeds while keeping dimpling constant. It was found that there is a 26.1% chance that the two speeds resulted in the same effect on the coefficient of drag. Next, the physical item no dimpling was kept constant, and it was found that there was a 42.3% chance that the two speeds have the same effect on coefficient of drag. This supports the expected results. Next, a paired t-test was carried out between dimpled and non-dimpled data while keeping low speed constant. It was found that there was a 98.2% chance that dimpled and non-dimpled designs have different effects on drag coefficient. When high speed was kept constant, it was found that there was a 99.5% chance that dimpled and non-dimpled designs have different effects on the coefficient of drag. This supports our results as the dimpled designs had higher coefficient of drag than the non-dimpled.
The first conclusion being that coefficient of drag is independent of velocity. The second conclusion being that both body design and dimpling will have an effect on the coefficient of drag. This means that by varying the body design on our vehicle for the Shell Eco Marathon, we will be able to lower the coefficient of drag accordingly.